Imagine you are sitting on a train, looking out the window, and trees, houses, poles are flashing outside the window. You feel the movement. Now imagine that you are on a train, but the windows are painted over with black paint. You can't see where you're going. You don't even know you're moving until you suddenly feel a slight jolt on a turn. Humanity is in approximately this situation right now. We're flying through space at an insane speed of 600 kilometers per second. This is almost 2 million kilometers per hour for comparison. The fastest aircraft in the world barely accelerates to 3,500 kilometers per hour, and we, together with the Earth, the Sun, and the entire Milky Way, are rushing in the direction of something huge, something invisible. And here's the creepiest thing, we don't know what it is. Scientists call this thing the Great Attractor. Sounds like the name of a villain from a science fiction movie, right? But this is reality. Something massive, something incredibly heavy, is pulling in our galaxy and thousands of other galaxies around it. It attracts with its gravity like a magnet attracts iron filings, and we've been flying there for billions of years. Let's figure out what's going on, why we only recently found out about it, and whether we should panic. Let's start with a simple question. How can you even understand that you are moving in space? On Earth, everything is simple. You look out the window, see the landscape that is changing, but there are no fixed landmarks in space. There are no poles, no road signs, no GPS. How did astronomers even understand that we were flying somewhere? The answer lies in the light, more precisely in how light changes when its source moves. You've probably heard the Doppler effect. When a car with a siren passes you, the sound is first higher, then lower. It's the same with light. As an object moves away from us, its light shifts to the red side of the spectrum. This is called redshift. When it approaches, it turns into a blue shift. At the beginning of the 20th century, astronomers began to study the light from distant galaxies, and they noticed a strange thing. Almost all galaxies have a redshift, that is, they are moving away from us. The universe is expanding, a discovery that blew up science. But then scientists took a closer look and they found that some galaxies behave strangely. Imagine that you are standing on a moving escalator in a shopping center. The escalator goes up. This is the expansion of the universe. All the people on the escalator go up with him. But suddenly you notice that one person on the escalator is running down. It goes up anyway because the escalator moves up, but slower than the others, and the other person runs upwards. He rises the fastest. This is approximately what astronomers saw. Some galaxies are moving away from us more slowly than they should according to the laws of the expansion of the universe. And some are faster. This means that some additional force is acting on them, something pulls them or pushes. In the 1970s, a group of astronomers decided to map the velocities of galaxies around us. They measured the red and blue shifts of hundreds of galaxies, trying to understand where and at what speed they were moving. And that's when the strange things began. It turned out that our Milky Way is not just drifting in space. It rushes in a certain direction at a tremendous speed. At first, we thought that this was an accident, a measurement error. But no, the data has been confirmed over and over again. We are moving, and very quickly. Astronomers have begun to calculate exactly where we are going, and they realized that the direction was the constellation Centaurus and the constellation Vela. They're at a distance of about 150 to 250 million light-years from us. There must be something massive, something with such monstrous gravity that it pulls not only our Milky Way but thousands of other galaxies around. This discovery was made in 1986 by astronomers led by Donald Lindenbell and his colleagues. They called this area the Great Attractor, an attraction, a thing that attracts us. But here's the problem. We can't see it. Why? Because the Great Attractor is just beyond the disk of our own galaxy. Imagine that you are trying to see something on the other side of the room, but there is a huge wall of thick fog between you and this object. You know there's something out there, but you can't see the details. In our case, this wall is the avoidance zone of avoidance. This is the area of the sky that is hidden from our view by the disk of the Milky Way. Our galaxy is a flat disk with a huge amount of stars, gas, and dust inside it. When we look through this disk, light from distant objects is absorbed and scattered. It's like trying to see a street lamp through a thick fog. The light is there, but it's blurred, distorted, and you can't figure out what's there. Therefore, scientists worked almost blindly for a long time. They knew that there was something there, they calculated the approximate location, but they could not see. Then they began to use other methods. First, radio telescopes. Radio waves pass through dust better than visible light. It's like an ultrasound. It allows doctors to see the baby in the womb. Although the eyes can't see it, radio telescopes have begun to detect galaxies in the zone of avoidance, and the picture began to become clearer. It turned out that the Great Attractor is not one giant galaxy or black hole. As some have assumed, it is a huge cluster of galaxies, supercluster, such a concentration of matter in one place that its gravity can be felt hundreds of millions of light years away. To understand the scale, let's use an analogy. If our solar system were the size of a coin, then the Milky Way would be the size of Europa, and the Great Attractor is a region about half the size of the Earth, filled with thousands of galaxies, each containing billions of stars. Just try to imagine it. But the story becomes even more interesting because when scientists began to dig deeper, they realized that the Great Attractor was not the final point of our journey. In the 1990s, astronomers discovered that even the Great Attractor itself is moving. It is also flying somewhere. It was like a nesting doll. We thought we had found the answer, but it turned out that this was only the beginning of the puzzle. Scientists continued their observations and in 2014 made another stunning discovery. They found something they called Laniakea. It is a Hawaiian word that means vast heaven. Laniakea is a giant structure, a supercluster of galaxies, which includes our Milky Way, the Great Attractor, and hundreds of thousands of other galaxies. Laniakea is so huge that it contains the mass of about 100,000 trillion suns. Yes, you read that right, 100,000 trillion. It is a 1 followed by 17 zeros. And all these galaxies are moving towards the center of Laniakea, to the area called the Great Attractor. But even this is not the end of the story. Because Laniakea itself is attracted to an even more massive structure, Shapley supercluster, it is an even larger cluster of galaxies that is about 650 million light-years away, and it seems to be the one that creates the strongest gravitational pull in this region of the universe. That is, we get the following picture. The Earth revolves around the Sun revolves around the center of the Milky Way is moving towards the Great Attractor moves towards the center of Laniakea, and Laniakea is drawn to Shapley. It's a dance of gravity that involves billions of galaxies. Now let's talk about the most important question that is probably spinning in your head. Is it dangerous? Will we crash into anything? Is the end of the world near? Spoiler, no. First, the distances in space are so monstrous that even at 600 kilometers per second, it would take us billions of years to reach the Great Attractor. For comparison, the age of the universe is about 13.8 billion years. The age of the Earth is about 4.5 billion years. Dinosaurs became extinct only 65 million years ago, and we have been flying to the Great Attractor for billions of years, and we will fly billions more. Second, the universe is expanding, and it expands with acceleration. This means that the farthest regions of space are moving away faster and faster. At some point, the expansion of the universe will become so strong that it will outweigh the gravitational pull of the Great Attractor or any other structure. Galaxies will begin to fly away from each other faster than gravity can hold them together. It's a very strange feeling when you realize we live in a short historical moment in the universe when we can still see other galaxies in trillions of years. When the expansion has accelerated to the limit, our distant descendants, if there are any, will see only their own galaxy in the sky. Everything else will be hidden behind the event horizon, carried away by the expansion of space. To them, the universe will seem empty and lonely. But let's get back to the Great Attractor. There is another question. What is there at all? What creates such a monstrous gravity? Modern data show that in the region of the Great Attractor there is a huge cluster of galaxies, which is called the Cluster of the Square. It is one of the most massive clusters in our region of the universe. It contains thousands of galaxies, each containing billions of stars. Imagine a hive where each bee is a galaxy the size of the Milky Way. But that's not all. Scientists suspect that there is also a huge amount of dark matter there. Dark matter is a mysterious substance that does not emit light, does not absorb it, and does not interact with electromagnetic radiation in any way. We can't see it with any telescope, but we know that it exists because it has mass, and this mass creates gravity. According to current estimates, about 85% of all matter in the universe is dark matter. Ordinary matter, which makes up stars, planets, and you and me, is only 15%. Imagine an iceberg. The visible part above the water is ordinary matter, and the huge invisible part under the water is dark matter. The Great Attractor most likely contains a colossal amount of dark matter. It is she who creates the main part of the gravitational attraction. Ordinary galaxies that we see are like the tip of the iceberg. Most of the mass is hidden from our eyes. This begs the question, could we ever see the Great Attractor in its entirety? Send a probe there? Take a picture? With a probe, no, even if we were to launch a spacecraft at the speed of light, which is physically impossible, it would take 150 to 250 million years to get there, and then the same amount of time for the signal to return to us. Humanity in its current form will not exist for a long time. But it is possible to see it. Modern telescopes are becoming more and more powerful. The James Webb Space Telescope, which began work recently, is able to see in the infrared range. Infrared light passes through dust better than visible light. It's like a thermal imager. It shows heat through the walls. Perhaps with the help of such telescopes, we will be able to peer through the avoidance zone and finally see the Great Attractor in all its glory. Scientists also use radio telescopes and X-ray observatories. X-rays show hot gas between galaxies, which is also an indicator of massive structures. Gradually, like a detective story collecting evidence, astronomers put the picture together. Now let's talk about what all this means for our understanding of the universe. The Great Attractor and similar structures show us that the universe is not chaos. It is a complex, organized system where matter is unevenly distributed. There are huge voids, regions where there are almost no galaxies, and there are giant clusters where galaxies huddle together like sheep in a pen. This structure is called the cosmic web. If you could look at the universe from afar, you would see threads and knots like a spider's web. Filaments are chains of galaxies. Nodes are clusters and superclusters, such as the Great Attractor, and between them there are gigantic voids, practically devoid of matter. This structure was formed as a result of gravity. Immediately after the Big Bang, matter was distributed almost evenly, but not perfectly. There were tiny bumps, areas where there was a little more or a little less matter. Gravity began to pull matter toward regions with greater density. These areas became even denser, attracting even more matter. Thus, over billions of years, galaxies, clusters of galaxies and superclusters have formed. The Great Attractor is one of the nodes of this cosmic web. It shows us how gravity works on the largest scales in the universe. But there is another mystery. When scientists measure the speed of galaxies, they find strange anomalies. Some galaxies are not moving quite in the direction they should be moving under the influence of structures as we know them, such as the Great Attractor or Shapley. This gave rise to the hypothesis of the existence of even more massive structures beyond the observable universe, or that galaxies are affected by forces that we do not yet understand, perhaps dark energy. The mysterious force that accelerates the expansion of the universe is unevenly distributed, or there are some effects of quantum gravity that we haven't discovered yet. This is one of the most exciting things about science. Every answer raises new questions. We thought that the Great Attractor was the end point, but it turned out that it was only an intermediate station. We thought we understood gravity, but it turns out that on the largest scales it doesn't behave exactly as we expected. Let's talk a little bit about how it's possible to study something that's millions of light years away and hidden behind dust. Astronomy is a detective work. You do not have the opportunity to touch the object, come closer to it, and do the analysis. All you have is light, tiny photons that have traveled for millions of years to get into your telescope. But there is a surprising amount of information that can be extracted from this light. The light spectrum is like a barcode on a product in a store. It tells you what chemical elements an object is made of, what its temperature is, whether it is moving towards you or away from you, and how fast. Red and blue shifts are one of the main tools. If a galaxy moves away, its light shifts to the red side. If it is approaching, turn it into blue. From the value of the displacement, you can calculate the velocity. This is the basis of the foundations of cosmology. But there are other methods, for example, gravitational lensing. When light from a distant galaxy passes by a massive object, a galaxy cluster or a great attractor, its path is curved by gravity. It's like looking at an object through a glass of water. The image is distorted. From the degree of distortion, you can calculate the mass of the object that caused lensing. Astronomers also use cosmic microwave background radiation. It's an echo of the Big Bang, a light that was emitted when the universe was only 380,000 years old. This light carries information about the distribution of matter in the early universe. By studying tiny irregularities in this radiation, scientists can understand where the first galaxy clusters began to form. All of these methods together give us the ability to map the universe, even those areas that we can't see directly. Now let's talk about the human side of this story, because behind all these numbers and terms there are real people who have spent years, or even decades, of their lives trying to understand what the Great Attractor is. Astronomy is one of those sciences where results come very slowly. You can't just run an experiment in a lab and get an answer in a week. You need to wait until your application for the time of observations in the telescope is approved. It can take years. Then you are given several nights of observation, you collect data, then you analyze them for months, then you write an article, then it is reviewed, and only after that, if you are lucky, your discovery becomes known to the world. The people who discovered the Great Attractor worked with telescopes and computers that are primitive by modern standards. They manually measured the spectra of galaxies, manually calculated the redshift, and manually built graphs. This is painstaking, monotonous work that requires patience and faith that in the end you will find something important. And they found it. They discovered that the universe is much more complex and interesting than we thought, that even our own galaxy is just a small part of a huge, incomprehensible whole. When you look up at the night sky, you see the stars, several thousand stars. If the sky is dark and clear, all of these stars are part of the Milky Way. Our galaxy contains about 200 to 400 billion stars, and that's just one galaxy out of trillions in the universe. Now imagine that all these trillions of galaxies are not just static, they are moving, they dance the cosmic dance of gravity, attracting each other, forming structures hundreds of millions of light years across, and we are part of this dance. The Great Attractor is a reminder of our place in the universe. We are not the center of the universe, we're not even at the center of our galaxy. We are on the outskirts, in a quiet arm, orbiting an unremarkable yellow star. And this whole construct is hurtling through the cosmos to something that we are only beginning to understand. But here's the amazing thing, we can understand it. We, small creatures on a small planet, living ridiculously short lives by cosmic standards, can figure out what happens at distances of millions of light years. We can calculate a mass of objects that we will never see. We can predict the future of the universe trillions of years in advance. This is probably the most striking thing in this whole story. Not the Great Attractor itself, but the fact that we learned about it. Now let's think about the future. What awaits the exploration of the Great Attractor? What discoveries await us? First, new telescopes. James Webb is already working and showing amazing results. Ground-based telescopes of a new generation are being built. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, these giants will be able to see farther and clearer than any telescope before them. Secondly, new methods of observation. Gravitational waves are a completely new way to study the universe. In 2015, we detected gravitational waves from a black hole merger for the first time. It was like finding a new feeling. Previously, we only saw the universe, now we can hear it, and gravitational waves pass through any obstacles, including the avoidance zone. Perhaps with their help, we will be able to study the Great Attractor in more detail. Thirdly, computer modeling. Modern supercomputers can simulate the evolution of the universe from the Big Bang to the present day. They show how galaxies formed, how they collided, and how clusters formed. By comparing the results of the simulations with real-world observations, we can test our theories and refine the parameters of the model. But the most interesting thing is the questions to which we do not yet know the answers. For example, is the Great Attractor unique? Or are there many similar structures in the universe? Modern data show that galaxy clusters are commonplace, the universe is full of them, but each cluster is unique with its own history and structure. Or this, how does the Great Attractor affect the formation of galaxies in its vicinity? As galaxies fall into a cluster, they collide with other galaxies, their gas heating up and being ejected. This can stop the formation of new stars. That is, galaxy clusters are a kind of graveyards where galaxies come to die, but the details of this process are still being studied. And also, what will happen to the Great Attractor in the distant future? In billions of years, the expansion of the universe will break the bonds between galaxies. The clusters will begin to disintegrate, the stars will go out, the universe will become dark and cold. But this is so far in the future that we need not worry about it. The sun will go out much earlier, in some 5 billion years. There is also a philosophical aspect to all this. The Great Attractor reminds us that we are not in control. We are flying through space, carried away by forces that were at work long before the appearance of mankind and will continue to operate long after we disappear. But this is not a reason for despair. On the contrary, this is a reason for admiration. We live in a universe that is full of wonders, a universe that follows clear laws, but at the same time constantly surprises us, a universe that is so vast that our minds can hardly grasp it, but we can study and understand it. Think about it. Every atom in your body was created in the bowels of a star, carbon, oxygen, nitrogen, all elements heavier than helium, all formed in thermonuclear reactions inside stars or during supernova explosions. You are literally made of stellar matter. And this stellar matter gathered into the planet on which life originated, and life evolved, and eventually there were creatures capable of asking the question, where did we come from and where are we going? And these beings, using telescopes and mathematics, found that they were hurtling through space to something called the Great Attractor. It's an amazing story when you think about it. Now, let's dive a little deeper into the physics of the process. How exactly does gravity make galaxies move? Gravity is the curvature of space-time by massive objects. This is a concept that Einstein introduced in his general theory of relativity. Imagine a tightly stretched fabric. If you put a heavy ball on it, the fabric will bend. If you now put a small ball next to a large one, it will roll down the slope to the big ball. This is how gravity works. Massive objects, stars, galaxies, clusters of galaxies, warp the space around them. Other objects, falling into this region of curved space, begin to move along curved trajectories. We call it gravity, but it's really just taking the shortest path in curved space. The Great Attractor is such a massive object that it warps space in a huge area around it. Galaxies, falling into this region, begin to move towards the center of curvature. This is not an instant process. This is a slow drift that lasts for billions of years. But here's the interesting thing. Gravity acts instantaneously at any distance. No, wait, that's not entirely true. According to the theory of relativity, gravity travels at the speed of light. If the sun suddenly disappeared, we would continue to orbit it for another 8 minutes, which is how long it takes for light to travel from the sun to Earth. But for slow-moving objects such as galaxies, this effect is almost imperceptible. The gravity of the Great Attractor acts on us here and now, because it has been in its place for hundreds of millions of years, and any changes in its structure would propagate to us at the speed of light, but in that time they would have already arrived. There is one more interesting point. A speed of 600 kilometers per second seems huge, and it is really huge by human standards, but on a cosmic scale, this is not so fast. The Earth rotates around the Sun at a speed of about 30 kilometers per second. The Sun rotates around the center of the Milky Way at a speed of about 220 kilometers per second, and the entire Milky Way is moving towards the Great Attractor at a speed of 600 kilometers per second. This is the sum of all these motions plus the motion of the galaxy cluster to which the Milky Way belongs. So when you're sitting in your chair reading this, you're actually hurtling through space at incredible speeds. You rotate with the Earth, you fly around the Sun, you go with the Sun around the galaxy, and the whole thing is hurtling towards the Great Attractor. You are a space traveler without even moving. Now let's talk about how the discovery of the Great Attractor changed our picture of the world. Prior to this discovery, scientists thought that the universe was expanding uniformly, that all galaxies are moving away from each other at predictable speeds. It was a simple and elegant picture. But the Great Attractor showed that everything is much more complicated, that galaxies are subject to local gravitational forces, which can be stronger than the expansion of the universe on certain scales, that the universe is not a homogeneous expanding substance, but a complex system of interacting structures. This forced scientists to revise their models. They began to take into account not only global expansion, but also local movements. They began to build more detailed maps of the distribution of matter, and these maps showed an amazing picture. The universe resembles foam or a sponge, with voids and filaments, clusters and superclusters. This discovery also confirmed the importance of dark matter. Without dark matter, the gravity of visible matter would not be strong enough to explain the motion of galaxies. Dark matter is the invisible glue that holds the universe together. But the most important thing is that the Great Attractor has shown us the limits of our knowledge. We thought we understood how the universe works, but it turns out that we only see a small part of it, that most of the universe is hidden from us: dark matter, dark energy, the regions beyond the avoidance zone. This is a lesson in humility, but it is also a lesson in hope, because each new discovery shows that the universe is even more interesting than we thought, that new mysteries and new answers await us ahead. There is one more aspect that is worth talking about. How does the Great Attractor relate to the future of humanity? At first glance, this is a purely scientific topic: fundamental physics, cosmology, things that don't affect our daily lives. But this is not entirely true. Understanding how the universe works gives us a context for our existence. It shows us that we are part of something much bigger, that our history began not 10,000 years ago with the emergence of civilization, but 13.8 billion years ago with the Big Bang. This understanding affects how we see ourselves and our place in the world. It can inspire us, it can frighten us, it can make us think about the meaning of life. In addition, exploring the Great Attractor is a technological challenge. To study such distant objects, you need super powerful telescopes, supercomputers, and new detectors. The development of these technologies often leads to side effects that find application in everyday life. For example, CCD sensor technology, which is used in digital cameras and smartphones, was developed for astronomical observations. Image processing algorithms that improve the quality of photos in low-light conditions also came from astronomy. Medical tomography uses principles similar to those used to map the distribution of matter in the universe. So exploring the Great Attractor isn't just about satisfying curiosity. This is an investment in the future, in technology, in our understanding of the world. And one more thing. The Great Attractor reminds us of the importance of long-term thinking. In a world where everything is measured by quarterly reports and news cycles, where people think a year or two ahead, astronomy makes you think billions of years ahead. This broadens the horizons of planning. It makes us think about the long-term consequences of our actions. If we can predict the movement of galaxies billions of years in advance, maybe we should think about the future of our own planet for the same time. Of course, humanity will not exist for billions of years in its current form, but a civilization that could have evolved from ours or artificial intelligence or something else, who knows? The Great Attractor also poses existential questions to us. If our entire galaxy is just a speck of dust dragged away by the gravity of a huge cluster, what does this say about our importance? About the meaning of our life? Some people find this a reason for nihilism, like, if we are so insignificant on the scale of the universe, then what difference does it make what we do? But you can look at it in another way. Yes, we are small, but we can understand that we are small. We can measure the distance to the Great Attractor, calculate its mass, and predict its future. This is an amazing ability. Carl Sagan, the great popularizer of science, said, We are the way the cosmos knows itself. And this is true. The universe has existed for billions of years, but it was only with the advent of intelligent life that it became aware of its existence. We are the eyes and ears of the universe. Through us, she looks at herself, and this makes us not insignificant, but, on the contrary, incredibly important. There is one more interesting detail. The name, the Great Attractor, and attraction sounds almost mystical, right? As if it is some kind of living creature that attracts us on purpose. Of course, this is not true, it's just gravity, impersonal physical strength, but the name reflects our human perception. We tend to personify natural phenomena, to give them human features. The ancient Greeks believed that the stars were deities, that thunder is the wrath of Zeus, that eclipses are signs of the gods. We got away from it. We realized that nature follows the laws, not the whims of the gods. But even now, when we call a cluster of galaxies the Great Attractor, we give it a certain power, a certain will, although in fact it is just an accumulation of matter that has mass, which means it creates gravity. Language matters. The way we call things affects how we perceive them, and scientists understand this. They try to give objects descriptive names that reflect what they are. The Great Attractor is an object that attracts. A black hole is a region from which nothing can escape. A neutron star is a star made up of neutrons. But sometimes the names are also poetic. Laniakea is the boundless heavens, Veronica's hair cluster, Andromeda Nebula. These names remind us that science is not just about formulas and numbers. It is also beauty, admiration, an attempt to find words to describe what cannot be described. Let's now talk about what we don't yet know about the Great Attractor, because the list of the unknown is much longer than the list of the known. We do not know the exact mass of the Great Attractor. There are estimates, there are approximate figures, but there is no exact number. This is because we can't see the entire structure, and because most of the mass is dark matter, which we can't observe directly. We don't know the exact structure. How many galaxies are there? How are they distributed? Are there supermassive black holes there? What is the history of the formation of this cluster? We do not know exactly how the Great Attractor interacts with other structures. How does it affect Shapley supercluster? How does it interact with other clusters in Laniakea? We don't know if there are other objects in the universe that are similar to the Great Attractor. Most likely, there is. The universe is huge, and it would be strange if such a structure were unique, but we have not yet found them or have not studied them in sufficient detail. We do not know how the Great Attractor will develop in the future. Will it grow, swallowing more and more galaxies? Or will the expansion of the universe stop this process? Or will it eventually disintegrate when dark energy becomes the dominant force? All these questions are directions for future research. This is work for the next generations of astronomers, who will have more powerful instruments and perhaps a deeper understanding of physics. There is another topic worth touching upon: alternative theories, because in science, there is always room for doubt and alternative explanations. Some scientists suggest that the motion of galaxies can be explained not only by gravity, but also by other effects, for example, the uneven distribution of dark energy, or errors in our measurements of the distances to galaxies. There are also more exotic theories, for example, that our universe is just one of many universes in the multiverse, and that the Great Attractor is the result of gravitational interaction with a neighboring universe. It sounds like science fiction, and there's no evidence to support the idea at this point, but who knows? Maybe future discoveries will show that this is not so crazy. Or here's another thing. Some physicists suggest that gravity on very large scales may not work exactly as described in general relativity, that there are some quantum effects or extra dimensions that affect the motion of galaxies. These theories have not yet been confirmed, but they are being developed and tested. Science develops through doubt, by testing alternative hypotheses, through constant clarification and revision of our ideas, and the Great Attractor is a perfect example of an object that makes us doubt and look for better explanations. Now let's take a step back from pure science and talk about the cultural influence of the Great Attractor. Although it is a relatively obscure topic outside of the scientific community, the Great Attractor has appeared in various works of popular culture, in science fiction novels, in movies, in video games. It is usually depicted as some mysterious force that threatens the universe, or as an ancient artifact of an alien civilization, or as a portal to another dimension. All of these are fantasies, of course, but they show that the idea of something huge and invisible that draws us and captures people's imaginations. There is something primal in this fear of the unknown, fear of forces we don't control. Our ancestors were afraid of thunder, lightning, earthquakes, natural forces that they did not understand. We have moved away from this. We have understood the physics of these phenomena. But the Great Attractor reminds us that there are things that are still beyond our comprehension. And that's okay. This is even good, because it is the incomprehensible that moves science forward. It is the questions to which we do not know the answers that make us build telescopes, conduct experiments, and develop new theories. The Great Attractor is also a reminder that the universe doesn't have to be intelligible to us. It is not made for our convenience. It simply exists, following its own laws, and the fact that we can at least partially understand these laws is already an incredible achievement. There is another important aspect. Education. The Great Attractor is a great topic to get people interested in science, especially young people. When you tell a student that we are hurtling through space to something huge and invisible, his eyes light up. This is not boring physics from a textbook. It's an adventure. This is a mystery. This is something that can be imagined, something that can be dreamed about. And through this interest, it is possible to lead a person to a deeper understanding of science, explain what redshift is, what is gravity, what is dark matter, to show how scientists make discoveries, how they test their theories, how they admit mistakes and look for new answers. The Great Attractor is the gateway to the world of science, and the more people who pass through this gate, the better for all of us, because science is not just a collection of facts. This is a way of thinking. This is the ability to ask questions, look for evidence, change your mind under the influence of new data. And these skills are useful not only in space exploration, they are useful in everyday life, in the assessment of news, in decision-making, in understanding the world around us. Let us now talk about the practical aspects of studying the Great Attractor. How exactly do scientists work on this problem? The first step is observations. Astronomers collect data using telescopes. These can be optical telescopes that work in visible light, radio telescopes that pick up radio waves, infrared telescopes that see heat, X-ray observatories that record high-energy radiation. Each type of telescope gives a different part of the picture. Optical telescopes show stars and galaxies. Radio telescopes see gas and dust. Infrared penetrate dust and show hidden areas. X-rays show hot gas and active galactic nuclei. All this data needs to be collected, processed, and analyzed. This is a huge job. Modern telescopes generate terabytes of data every night. This data needs to be stored, cataloged, and made available to researchers around the world. The second step is analysis. Scientists use computer programs to process data. They measure the redshift of galaxies, calculate their velocities, and determine distances. They build maps of the distribution of matter, look for patterns, try to understand the structure. This requires not only powerful computers, but also complex algorithms. Machine learning and artificial intelligence are increasingly being used in astronomy. Programs learn to recognize galaxies in images, classify them by type, and find anomalies. The third step is modeling. Scientists create computer simulations of the universe. They set the initial conditions, the distribution of matter after the Big Bang, and run the simulation. The computer calculates how gravity will act on each particle of matter, how galaxies and clusters will form. These simulations are compared to real-world observations. If the simulation produces results similar to what we see in reality, then our model is correct. If not, you need to look for a mistake. Maybe we've misjudged the amount of dark matter, or they incorrectly accounted for the influence of dark energy, or there are some effects that we did not take into account at all. The fourth step is to publish the results. Scientists write articles in which they describe their discoveries. These articles are peer-reviewed, with other scientists checking the work, looking for errors, and asking questions. Only after that the article is published in a scientific journal. And the fifth step is discussion. The scientific community discusses the results at conferences, in discussions, in new articles. Someone agrees with the conclusions, someone offers alternative explanations. In this way, a consensus is gradually formed, a common understanding of the problem. This is a slow, painstaking process, but that's how science works, not through the insights of lone geniuses, but through the collective work of thousands of people around the world, who step by step are approaching the truth. And the Great Attractor is part of that process. This is one of the many mysteries that scientists are working on, and each new discovery brings us closer to understanding how the universe works. But here's the important thing to understand. We'll never know everything. The universe is too big, too complex. There will always be unanswered questions. There will always be areas that are inaccessible to our study. And that's great, because it means that there will always be work for researchers. There will always be new mysteries to solve. There will always be a reason to look up at the sky and wonder. The Great Attractor is not just a cluster of galaxies hundreds of millions of light years away. It is a symbol of our desire for knowledge. It's a reminder that we live in an amazing universe full of wonders. And the fact that we are rushing towards it at a speed of 600 kilometers per second is not a threat. It's just a fact, one of the countless facts about our reality. We are flying through space. We always flew, and we will always fly. This is our nature, the nature of everything in the universe: movement, change, evolution. The Great Attractor draws us towards him, but we are not passive victims of this force. We are observers, researchers, thinkers. We can understand what is happening to us, and that makes us special. So the next time you look at the night sky, remember, you're not just standing still. You race through space at incredible speeds, dragged by the gravity of an invisible giant. You are part of a cosmic dance that has lasted for billions of years. And you can understand that, you can find out about it, you can admire it. This is the greatness of the human mind. This is our contribution to the universe. We are small, but we can understand the big, and this is our strength.